Entropy illusion. All transactions on the Ethereum blockchain are deterministic state transition operations. This means that every transaction modifies the global state of the Ethereum ecosystem in a calculable way, with no uncertainty. This has the fundamental implication that there is no source of entropy or randomness in Ethereum. Achieving decentralized entropy or randomness is a well-known problem for which many solutions have been proposed, including RANDAO, or using a chain of hashes, as described by Vitalik Buterin in the blog post Validator Ordering and Randomness in POS. The vulnerability. Some of the first contracts built on the Ethereum platform were based around gambling. Fundamentally, gambling requires uncertainty, in other words, something to bet on, which makes building a gambling system on the blockchain rather difficult. It is clear that the uncertainty must come from a source external to the blockchain. This is possible for bets between players. See for example the commit-reveal technique. However, it is significantly more difficult if you want to implement a contract to act as the house, like in blackjack or roulette. A common pitfall is to use future block variables. That is, variables containing information about the transaction block whose values are not yet known, such as hashes, timestamps, block numbers, or gas limits. The issue with these are that they are controlled by the miner who mines the block, and as such are not truly random. Consider, for example, a roulette smart contract with logic that returns a black number if the next block hash ends in an even number. A miner or miner pool could bet $1 million on black if they solve the next block and find the hash ends in an odd number. They could happily not publish their block and mine another until they find a solution with the block hash being an even number, assuming the block reward and fees are less than $1 million. Using past or present variables can be even more devastating, as Martin Swen demonstrates in his excellent blog post. Furthermore, using solely block variables means that the pseudo-random number will be the same for all transactions in a block, so an attacker can multiply their wins by doing many transactions within a block, should there be a maximum bet. Preventive techniques. The source of entropy, or randomness, must be external to the blockchain. This can be done among peers with systems such as commit-reveal, or via changing the trust model to a group of participants, as in RANDAO. This can also be done via a centralized entity that acts as a randomness oracle. Block variables should not be used to source entropy, as they can be manipulated by miners. Real-world example: Prng contracts. In February 2018, Arseny Rutov blogged about his analysis of 3,649 live smart contracts that were using some sort of pseudo-random number generator, Prng. He found 43 contracts that could be exploited. External contract referencing. One of the benefits of the Ethereum World Computer is the ability to reuse code and interact with contracts already deployed on the network. As a result, a large number of contracts reference external contracts, usually via external message calls. These external message calls can mask malicious actors' intentions in some non-obvious ways, which we will now examine. The vulnerability. In Solidity, any address can be cast to a contract, regardless of whether the code at the address represents the contract type being cast. This can cause problems, especially when the author of the contract is trying to hide malicious code. Let's illustrate this with an example. Consider a piece of code like ROT13 encryption.sol, which rudimentarily implements the ROT13 cipher. This code simply takes a string, letters A to Z without validation, and encrypts it by shifting each character 13 places to the right, wrapping around Z. In other words, A shifts to N and X shifts to K. The assembly in the preceding contract does not need to be understood to appreciate the issue being discussed, so readers unfamiliar with assembly can safely ignore it. Now consider the following contract, which uses this code for its encryption. Import ROT13 encryption.sol. Contract encryption contract open brace ROT13 encryption library. Constructor with one parameter ROT13 encryption library. Open brace encryption library equals encryption library. Close brace. Function encrypt private data with one parameter string private info. Open brace encryption library.rot13 encrypt of private info. Close brace. Close brace. The issue with this contract is that the encryption library address is not public or constant. Thus, the deployer of the contract could give an address in the constructor that points to another contract. For example, this other contract can implement the ROT26 cipher, which shifts each character by 26 places, in other words, does nothing. More simply, the attacker could have linked to the following contract, which prints out the text. If the address of either of these contracts were given in the constructor, the encrypt private data function would simply produce an event that prints the unencrypted private data. Although in this example a library-like contract was set in the constructor, it is often the case that a privileged user, such as an owner, can change library contract addresses. If a linked contract doesn't contain the function being called, the fallback function will execute. For example, with the line encryption library.rot13 encrypt invoked with no argument, if the contract specified by encryption library was contract blank open brace event print with one parameter string text function with no parameter open brace emit print with one argument here close brace, then an event with the text here would be emitted. Thus, if users can alter contract libraries, they can in principle get other users to unknowingly run arbitrary code. Warning: the contracts represented here are for demonstrative purposes only and do not represent proper encryption. They should not be used for encryption. Preventive techniques. As demonstrated previously, safe contracts can in some cases be deployed in such a way that they behave maliciously. An auditor could publicly verify a contract and have its owner deploy it in a malicious way, resulting in a publicly audited contract that has vulnerabilities or malicious intents. There are a number of techniques that prevent these scenarios. One technique is to use the new keyword to create contracts. In the preceding example, the constructor can be written as constructor with no parameter, open brace, encryption library equals new ROT13 encryption, invoked with no argument, close brace. This way, an instance of the reference contract is created at deployment time, and the deployer cannot replace the ROT13 encryption contract without changing it. Another solution is to hardcode external contract addresses. In general, code that calls external contracts should always be audited carefully. As a developer, when defining external contracts, it can be a good idea to make the contract addresses public to allow users to easily examine code referenced by the contract. Conversely, if a contract has a private variable contract address, it can be a sign of someone behaving maliciously, as shown in the real-world example. If a user can change a contract address that is used to call external functions, it can be important in a decentralized system context to implement a time lock and/or voting mechanism to allow users to see what code is being changed, or to give participants a chance to opt in or out with the new contract address. Real-world example: Reentrancy Honeypot. A number of recent honeypots have been released on the mainnet. These contracts try to outsmart Ethereum hackers who try to exploit the contracts, but who in turn end up losing Ether to the contracts they expect to exploit. One example employs this attack by replacing an expected contract with a malicious one in the constructor. This post by one Reddit user explains how they lost 1 Ether to this contract by trying to exploit the reentrancy bug they expected to be present in the contract.